Otherwise, hardware, I'm going to go through some stuff to make sure we're all on the same page and you understand the rest of the hardware limits. Okay? Status word 1, 0, let's get back to it. Bus voltage fault, we already talked about high and low bus voltage, but you don't know which one you hit. If you go down in the status words, you'll actually find the high and low bus voltage fault. Here's bus voltage saturation. That's a little bit different. That's actually when you're going at 100% torque and you got back EMF saturation. I can't remember what the other one is. There we go. Status word 6, low bus voltage, high bus voltage. Low is set at 8 volts, high is at 72. That's one of the ones that tell you which one it is. Okay? Hardware-wise, that's where you find them. Okay? Let me go back to 0 again. Okay? I'm trying to just stick with hardware stuff because that's what this discussion is about. We already talked about hardware limits. Software limits aren't hardware, but you have a match for software limits. None of these are actually fault conditions, but they tell you the indication of an internal or external hardware index faults. You can assign external inputs to an index fault off of an external encoder, and you can see it through the status lists. If you want more details, I can tell you later. These bits do cover both hardware and software. Error channel 0 means there's an error on the 232 port. Error channel 1 is the 485 port. And of course, CAN error is any device net or CAN open motor or combination. Ethernet error, we actually do have an Ethernet motor in class 5, but it's a class 4 gateway type product, so it's not that great. Hardware-wise, we have an internal chip for an EEPROM for data storage. This says I2C running. Earlier I showed a block diagram for the CPU. In reality, here's the CPU, and there's an extra memory chip over what's called an I2C bus. Okay? That talks to this EEPROM. In this EEPROM, we're sectored off the 32K of user storage for programming and another 32K for general data storage. An external device such as a PLC or an HMI or a PC can talk through the 232 port and send data to and from this section of memory. Okay? You can also do it within a program. So within this program, the CPU may read a command sequence that says write to this section. Well, you don't want those colliding. Okay? So what we've done is, where the hell did I go? You don't want to override that. So you may have to put a program in your motor that monitors that bus to see if anyone is actively talking to it. That prevents you from having a collision over that I2C hardware bus. Okay? ADB checksum, we already talked about that. Program running, that's not hardware, I don't want to talk about that yet. EE write buffer overflow. Okay? You can flood the buffer if you try to write too much in one shot. That's all that's really telling you. You can also get a buffer overflow or underflow on the COM channels as well, and those bits will go off. So each of those covers your buffers. That's all the hardware on that one. Let's see what we got next. Okay, we talk a little bit about this. Torque and voltage saturation. You're only getting voltage saturation in an AC product that we don't have yet delivered to the open public. Torque saturation, you can get on this one now. Torque saturation means for the given demand, you have saturated as much out of the PID filter as it can command to the drive as possible. It can't give any more. That torque saturation bit says I'm working as hard as I can. It in and of itself does not cause a fault. Okay? If you're going as fast and hard as you can, but it's not fast enough, the next thing you drop back to is possibly peak current, then continuous current, possibly thermal limit, and most likely a following error. You're trying as hard as you can't go any faster, you're falling behind, you're going to reach an error limit and fault out. So that torque saturation probably will come just before you get a position error. You may never notice it because it shows up as a dynamic indication and immediately goes away. It's self-resetting. Okay? Wraparound occurred. Anybody have an idea what wraparound means? Nobody? That's 32-bit max counting what we have on the internal encoder. Plus or minus 2 to the 31st, plus or minus 2.4 billion encoder counts. Anytime you wrap over that, that wraparound will occur. Okay? You have something called velocity direction and torque direction. I had them add this in firmware probably 4 years ago when we first started doing Class 5. The reason being is you may want to know if you're driving forward or reverse. You may want to know that if you excel up to speed and you start getting velocity ripple due to changes in load, which side of the curve you're on. Okay? If you're going in the positive direction, the bit will be on. When you're going to the negative, it'll be off. Okay? For a given direction. That's what that's about. Torque direction's the same way. You can actually be going in the positive direction and be commanded a negative torque trying to slow down. So that bit can be on or off in either direction. It doesn't matter. It's basically telling you which way it's trying to go compared to where it's actually going. Am I trying to speed up? Am I trying to slow down? Am I trying to add more force or subtract from that force? That's what these give you. I/O fault latch, that's the expanded I/O connector on the back of the motor. Okay? This expanded I/O connector, it does have overcurrent and thermal shutdown. If you get an I/O fault latch, the only way to clear this I/O fault latch is to power down and reset that chipset. Not the whole motor, but just the external I/O. It is the only way to clear that. Okay, I'm going to repeat it again. The only way to clear an I/O fault latch, which applies to external I/O, is to power down that 12-pin connector and bring it back up. Okay, that's for safety's sake. So if somebody goes out there and they put a 10-amp load on a 300 milliamp channel, they're going to get an I/O fault latch. They're going to turn it off, turn it back on, and if the load is because they shorted out the wires, it's just going to keep faulting and resetting. The chip will protect itself by shutting itself down. You will get the indication by I/O fault latch, and there's nothing you can do other than turn it off and back on again and hope it clears and find out what's causing the problem externally. Okay? Relative position mode, that's not really hardware. X-stop and progress, that can be hardware. Under the case that you get a travel limit set to cause a deceleration, when you get a travel limit, that X bit will show up because it will decelerate on the stop. That's by design in hardware as an option for how to deal with a fault condition on travel limits. Okay? Peak current saturation. That's an absolute indication of 100% PWM. Okay? It's a peak saturation current. It's an indication that the op-amp reading that came back saturated. It shows we meet or exceed the absolute maximum current. Okay? Modular rollover. That's a limit nest software, but I'll just tell you what it is. You can set a module count to keep repeating a certain number of counts. That just tells you what it is. Okay? Hardware-wise, brake asserted and brake on. That's internal pin that controls an internal brake if you've got one, or if you redirect the signal to an external pin, it will tell you you're supplying power. Okay? The reason it says brake asserted and on, that means you've got the brake enabled to turn on automatically, and right now it's sending a positive signal to disengage the brake. Because brakes are typically fail-safe, you have to supply power to disengage it and allow the motor to turn. Okay? So that's what this is about. External input go enabled. What the heck is that? That's a hardware feature that says, I want to make one of these inputs appear like the G command. When you enable that function, that means one of those inputs, if you give it a signal, it's the same thing as giving a go command at the terminal screen or inside the program. So that is a hardware feature. Velocity target reach, that's not really a hardware feature, that's a firmware deal. That just tells you you reach the velocity that you want to go to. If you command a certain velocity, it tells you when you reach it. Okay?
So if you write a program that uses an input for go, that's when that will automatically enable?
Well, no. What will happen is if you set the command, and I think it's, I don't even know what the command is. I think it's UG and a number. I can't remember. I don't remember the command offhand, but once you enter that, from that point on, that particular input, if you ground it, if it's 5 volts, or if you supply 24 volts to the 24 volt one, it's no different than typing G and pressing enter. There's no difference. The motor's oblivious to it. That's just telling you that you enabled that function. You've now assigned that hardware to the go command. Okay, that's what that's about. Okay, another hardware function we have an internal clock. And in that clock, we can parse off and sample 4 independent timers. These are indications of those timers. Those timers are hardware-enabled clock timers, or I should say, it comes off the hardware system clock, which is firmware-enabled, but it's a feature you need to be aware of. And those timers are ready for anyone to use at any time. For instance, right now, if I say there's 4 timers, timer 0, 1, 2, and 3. TMR means timer. 0 would be the first timer. 1, 2, or 3 would be second, third, or fourth timer. And if I say 10,000, I just set a timer to start when I press the enter key and count down from 10,000 milliseconds to 0. So I hit the enter key, you see timer active. Now I'm counting down and down and down, and right now I don't know where it is, but eventually 10 seconds later, that timer's going to go inactive. Okay? There it went. So if I end up doing that again, there's timer that was on 10,000, TMR 1, comma, say 5,000. Now that one's on. I don't know when relative to the other one, I don't know which one's going to stop first. There's timer 2, or timer 1's now inactive. Okay? They are countdown timers. They are based off the hardware system clock. They are extremely accurate. They are accurate to a millisecond. And within that millisecond, they're accurate to less than 62 microseconds. So they're extremely accurate timers. 4 independent timers, you can use them for what you want. Later this week, we're going to learn about interrupts and how we can use interrupts on these timers to trigger other events. Okay? Let's see here. Interrupts. Mentioning timers and interrupts. This is more of a software feature we'll talk about later, but you can set different interrupts to trigger off on any of these other status bits, any hardware or software status bits. Like I said, we'll talk about those more later. Okay, here's some stuff we definitely need to cover in detail. Where's our break? Our break's right now. I'll tell you what, it's a good time to break.